You know what you signed up for when you clicked on this video. So without further ado, here's where the best slope and intercept come from in a regression with a single predictor. The goal of regression is to produce a line that fits given data points the best. To measure which slope and intercept are the best, well, you need a measuring stick. Ordinary least squares, or OLS for short, does this by taking the vertical distance of every point to the line, squaring those distances, then adding them up, producing a single number. This number has a lot of names, but it's often called the sum of squared errors, or sum of squares for short. If this number is small, it means that the points are close to the line, which means a better fit between line and data points. So the best line would be the one that has the smallest possible sum of squared errors, hence least squares for short. Over time, there's been a variety of spin-offs like weighting data points, so this method has been deemed ordinary least squares. By changing the slope, you can change the sum of squared errors. Likewise, changing the intercept also changes the sum of squared errors. If you only have one predictor, there are convenient formulas for the slope and intercept of the line with the least squares, and this is how you derive it. To find which value of x achieves a minimum or maximum value for a function, take the derivative of your function with respect to x. Set it equal to 0, and solve for x. What are we trying to minimize in regression? The sum of squares. What will we take the derivative of and set equal to 0? The sum of squares. Since we need to know values for both slope and intercept, we'll need to take two derivatives. It doesn't matter which one we work out first, so we'll start with the intercept. Write out the sum of squares, the vertical distances from the data points to the regression line. Square those distances, add them up, and substitute it in the equation of the regression line using the slope and intercept we plan to find. The derivative is a linear operator, so we can take the derivative inside of the sum. The stuff inside of the sum is a function of beta 0, so following the chain rule, the 2 comes down, the function of beta 0 remains, and we multiply by the derivative of the function of beta 0. Distributing the negative and taking the derivative in terms of beta 0, you get negative 1. The rest of the terms are constant in terms of beta 0, so their derivatives are 0. Factor out the 2 and negative 1 outside of the sum for a bit of cleanup, and that's our derivative we'll use to find the best intercept. The next bit is the same process, except the derivative is in terms of beta 1 this time, the slope. Bring the derivative inside of the sum and use the chain rule. Distribute the negative and take the derivative of the last term, but with respect to beta 1 this time. yi and beta 0 are constant in terms of beta 1, so their derivatives are 0. The last term's derivative is negative xi. For cleanup, bring the negative 2 outside of the sum. The negative xi can't come along since it depends on I, but we can stick it in front of the other term. That's our derivative we'll use to find the best slope. The best intercept is the one that makes the derivative of the first equation 0. And likewise, the best slope is the one that makes the derivative of the second equation 0. So set these two equations equal to 0 and solve for the best beta 0 and beta 1. Again, this is generally how to find maximums and minimums of functions in calculus. But before we go any further, let's get rid of the negative 2's by dividing each side of each equation by negative 2, just to clean things up a bit. Let's start with the first equation. The derivative was in terms of beta 0 to find the best intercept. So let's solve for beta 0. First off, let's distribute the negative sign and the summation. Beta 0 is a constant and doesn't depend on I, so adding it up n times gets you n copies of beta 0, or n times beta 0. Beta 1 is also a constant and doesn't depend on I, but xi does, so we'll factor beta 1 out and leave xi where it stands. We're trying to solve for beta 0, so let's isolate the term with beta 0 by adding n times beta 0 to both sides. Dividing both sides by n isolates beta 0 on the right side. Finally, the sum of y over n is just the average of y. and the sum of x over n is just the average of x. Now, my crippling OCD won't let me have beta 0 on the right, so I like to rewrite this expression with beta 0 on the left. But now we have a nice formula for the best beta 0. The average of the y's minus the average of the x's times beta 1. Yeah, it's in terms of beta 1, so we'll need that next. Let's grab the second equation. The derivative was in terms of beta 1 in order to find the best slope. So let's solve for beta 1. You see beta 0 in there? Substitute in our expression for beta 0, so our equation is only in terms of beta 1. This is one method used to solve a system of equations just like this. Distribute the negative sign again, then factor out beta 1 from the last two terms. Instead of x bar minus xi, I want to write it as xi minus x bar. You'll see why later. To do this, all I have to do is factor out a negative 1. You can multiply the negative back through to see that you get back what we started with, if you're not convinced that works. Group the first two terms together, so you have yi minus y bar, just like xi minus x bar. Distribute the xi to both the yi minus y bar and the beta 1 and xi minus x bar. Then distribute the summation. Beta 1 is constant and doesn't depend on I, so factor it out of the summation. Add the term with beta 1 to the other side. And finally, to isolate beta 1, just divide by the summation attached to beta 1. Again, my overbearing OCD is going to force me to write beta 1 on the left. But now we have a clean formula for the best beta 1. But we can rewrite this a bit further to make it even easier to apply. And all we'll need are two identities to do this. Take a look at this summation first. It may not look useful, but wait on just a hot second. Multiply the terms out specifically by multiplying x bar by yi minus y bar, then xi times yi minus y bar. Don't distribute the xi and x bar further. Just leave the terms just like this. Distribute the summation across the two terms. X bar is a constant and doesn't depend on I, so go ahead and factor it out of the summation. Notice how the second summation is the sum of yi minus y bar. This is exactly 0, and there's a few ways to see this. Distribute the sum and write the sum of y bar as n times y bar, since y bar is just a constant. In general, an average is the sum over n. Multiply both sides by n, and you get that n times the average is equal to the sum. This is always true. This is called centering data. Subtracting the mean from each data point forces the mean to be 0, and the sum of yi minus y bar to also be 0. But since that term is 0, all we're left with is a familiar term, the same term that's in the numerator of the expression for the best beta 1. Can we do the same thing for the denominator? Absolutely. This time, look at this summation. Distribute xi and x bar from the first term to the second term. Again, do not distribute them further. Leave them just like this. Distribute the summation across the two terms, factoring out x bar in the second, since it's constant and doesn't depend on I. Notice that the sum in the second term, it's centered, just like the other summation, except for x instead of y. It's also 0, and for the exact same reason. To see this, distribute the sum, write the sum of x bar as n times x bar, and use the formula for an average to rewrite this as the sum of x. Notice that this term is 0, so all we're left with is the one term that is exactly the term that's in the denominator of the expression for the best beta 1. Looking back at the equation for the best beta 1, we can use the first identity to rewrite the numerator, and the second identity to rewrite the denominator. And now you have clean, convenient formulas for the best slope and best intercept for a regression line using one predictor. There's another equivalent formula for beta 1, sometimes called the shortcut formula or computational formula. If you want to see how to derive it, or you want to see any other derivations animated just like this, tell me in the comments below.